Hey, Chris, I'm sorry. I'm sorry to interrupt. Apparently, our voice isn't working or wasn't working. So my apologies, everyone. So we're gonna back up a little bit and we'll start over. I think I've now fixed the problem. I see the audio now working. At least I see the Skype desktop audio moving. I don't see the lavalier mic working. So let me see if I can figure out what's going on here. All right, hang on just a second. Let me check a couple of things. My apologies, everybody. All right, Chris, why don't you just say something real quickly so I can get a mic check? Okay, so we're still not getting a mic on you. So I'm not sure what's going on. So we will, sorry, everybody, give us just a couple of seconds here. So we've got the lav mic in our studio isn't working. Yeah, I just don't see it on the.
Oh, now it's working. So it wasn't selected? No, now it's working. I can see the meter. Okay, testing, testing, sound check, sound check. Yeah, I can't hear you now. All right, testing, testing. So my sound's working, but I can't hear you. Maybe that doesn't matter. But I can't hear you to ask another question. I can't hear you when you ask any questions. So that's not going to work. Okay. Okay, sorry about that, people. I'm going to rewind and answer, reframe the question and answer it. So the question was about whether the oceans or liquid bodies of water on Jovian moons, what conditions might make them habitable or suitable for life? The world people think about most often in this question is Europa, because we know it is overlaid with an ice crust all the way around the moon, and under that ice crust, which may be about 1 kilometer thick, there's a liquid water ocean tens of kilometers deep. We know this even though we can't directly observe the ocean from radar and magnetometer readings from orbiting spacecraft decades ago, actually. What conditions might exist in that water, and what might make it life tolerable? The water is going to have dissolved minerals and salts from the subsurface layer, the rocky material of the moon itself, and it's going to have a certain salinity and a certain acid to alkaline range. Now, life on Earth can tolerate enormous ranges in pH, ranging from essentially 0 to 11 or 12. So the range for life is enormous, and it's almost certain that the liquid oceans on Europa are within the range of tolerability of life on Earth. It's obviously a very cold ocean. It's kept liquid that far from the sun by pressure from the ice crust on top and by heating from the rocky material in the moon, because it's a fairly large moon of Jupiter. So it's, by all accounts, the oceans of Europa are potentially hosting biology. And there are other moons of Jupiter that might have liquid under a rocky crust. They're not quite as watery as Europa is. We also know there are moons of Saturn that might fit this bill, including Enceladus, the tiny moon of Saturn that has ice jet geysers indicating a liquid ocean underneath. So generally there's a fairly high likelihood that some of the moons in the outer solar system could be habitable and could indeed host biology. No, I think we're having a sound problem, so I can't hear the questions. Okay. It's a question about Penrose's theory that the Big Bang was not the beginning, that was an end of a prior universe. And that seems like a confusing statement. Penrose actually and Hawking, back in the 70s and 80s, put together a cosmological idea called the no-boundary theorem, the no-boundary cosmology, which basically argued that the Big Bang wasn't the beginning, that there was a sort of closed space-time surface that constituted the Big Bang. It's a way in general relativity of framing an origin for the universe that doesn't include a singularity, or it doesn't actually require a formal Big Bang idea. This no-boundary idea, this hypothesis, and this cosmology from Penrose and Hawking has fallen out of disfavor, because we think the universe did, in fact, have an origin, that space-time was not, if not a singularity, it doesn't have to be a singularity, but it was incredibly dense, and so you don't need a no-boundary condition to explain the origin of the universe. So this is a sort of theoretical idea in cosmology that has fallen out of favor because it doesn't quite fit the observations of the early universe. So I'm going to have to check questions and then answer them. Okay, I'll be waiting for the next question, but I'll... The question is, can you explain the moon wobble issue? I'm not totally sure what that question means, but I think it's referring to the precession of the moon's axis, spin axis, and that's simply caused by the interaction between the Earth and the moon. Remember, the Earth and the moon are in a very strong gravitational connection because they're tidally locked, so one face of the moon always pointing towards the Earth, and that same tidal locking also creates a torque on the moon, and it means that the moon is going to precess around its axis of rotation. Now, the Earth is also precessing, but the Earth is a much more massive body, so it's the Earth that causes the moon to wobble. It's a pretty subtle and small effect, but it's been known for actually quite a long time. Okay. I'm going to get questions now from the screen in front of me. Oops, no, the questions in the screen in front of me, Matthew, are reversed, so it's really hard to read. They're better to pull them onto the laptop. A new study that says that the moon wobble will affect the Earth's climate around 2030. I'm not aware of that study, so I'm afraid I'm going to have to pass on that question. So I can't comment meaningfully on it. A question is about quantum field theory and how it relates to astronomy and our knowledge of the universe. Quantum field theory is a fundamental ideas of physics that treats particles essentially as quantum entities and then their existence as fields. Just as we have an electromagnetic field and you can have gravitational field, so particles can exist as fields too. And quantum field theory is a way of calculating the properties of things that we think of as particles in terms of quantum fields. So quantum field theory doesn't really apply directly to observation and measurement of the universe. We just measure the contents of the universe and radiation within the universe. Where quantum field theory applies, or might apply, or must apply really, is in the Big Bang itself, in the creation of the universe. And we don't know how it applies there because we have no observations of any physical state of the universe that early in time where quantum field theory applies. So the answer is, doesn't apply directly to our universe except at the very origin where our theories are still incomplete. Okay, get the next question. What does ITER hold for the... Now, you're going to have to remind me, Matthew, look it up, what ITER is an acronym for. I just can't remember. Sorry, everyone, this is pretty clunky this week, and we're going to have to finish early anyway, so this is a bit of a slow session. Right. So ITER is the Europeans' International Fusion Reactor Project. It's led by the Europeans. America does have some involvement. Fusion has been a bit of a bust, really. For 50 years there's been fusion research with the idea of creating sustainable reactions that could lead to a clean power source, because when you have fusion as an energy source, you're using hydrogen or deuterium and you're making helium, pretty much as the sun does, and the only byproduct is heat and energy, which you extract for your power. So there's no radioactive byproduct of this reaction. So fusion energy is clean, and therefore it's viewed as a panacea, or a long-term solution to our energy issues. In fact, the technology to make fusion work in a sustainable way is extremely challenging, because fusion operates at temperatures of millions of Kelvin, and every substance known to humans vaporizes at well below those temperatures, so you can have a containment mechanism except with magnetic fields. So sustainable fusion reactions have only been exhibited by ITER or any of these partnerships for small fractions of a second. So the implications for astronomy are not large, because it's just a research project in physics and it's not really proven its worth yet as a power source. So this fusion, sustainable fusion, lies in the future, we think. I can maybe hear you now.
All right, are you able to hear me now?
Yeah, I can hear you.
Okay, thank goodness. Okay, so Alexander is on helping out getting things working again. So I will let him do that. Since you can hear me, I'll read the next question. Art Studio, who is on with us live, asked, how much do we currently know about the objects outside the solar system?
Well, the solar system is very nearby universe, and everything outside it is, of course, the stars in our galaxy and all the galaxies in the universe. So it's a very broad question, and the answer is a lot, because the astronomy beyond our solar system is quite sophisticated. The Gaia satellite that the Europeans have has mapped out the positions and motions in the sky of 1 billion stars, which is a big chunk of the Milky Way, about 1% of the nearby galaxy. And broader brushstrokes, we've mapped out our entire galaxy. We've also counted and mapped out the motions and positions of millions of galaxies, hundreds of millions actually, with deep imaging. So a big question and a simple answer is a lot. Most of astronomy of the 20th and 21st centuries has been involved in mapping out stars and galaxies in the universe, and we know an awful lot about those objects now.
So they still can't. Oh, actually, now I think everything seems to be working. So I was going to say they couldn't hear that last question that I asked, so you may still have to repeat things. But I think we are back online. So I'm a little bit behind on questions because I was trying to troubleshoot some things. So I'm just going to grab one real quickly here. So Andrew Johnson, who's on with us live, asks, could light from some of the objects we see in the night sky have been redirected by a massive object as much as 90 degrees?
An interesting question. So we know that mass bends light. That's general relativity. And gravitational lensing is an example of that. The amount of bending that light can do based on lensing is usually quite small. So the gravitational lenses we see from distant galaxies or mapped by the Hubble Space Telescope, those are usually deflection angles or bending angles that are tiny, like arc seconds or few arc seconds, maybe with a rich cluster of galaxies, tens of arc seconds or an arc minute. That's a tiny fraction of a degree, and turning light through a right angle is 90 degrees. So most gravitational lensing is orders of magnitude smaller than deflecting it by 90 degrees. The exception, of course, is black holes. There are orbits near black holes. There are orbits which will trap a photon. That's called the photon sphere at 2 times the Schwarzschild radius, and that's the distance at which a light beam literally goes into orbit around a black hole. And there's an orbit slightly outside that where you could arrange a deflection angle of 90 degrees. So yes, in principle and in theory, black holes can deflect light through a right angle. And in some situations, this may actually occur. We just haven't seen any yet.
The next question is from Scott Rollins, who's on with us live, who would like to know, have we ever seen a new star form?
We've seen stars form, not in real time, because even though it is a quite rapid process in astrophysics, star formation, that is the free fall collapse of a gas cloud and the ignition of a star, it takes tens or hundreds of thousands of years. So we're never going to be able to watch it play out in real time. However, we have seen places in the universe, like the Orion Nebula, where stars are forming right now, and we can pick the places in the nebula where we think that process is really playing out right now. To do that, we have to use infrared observation, especially far infrared, because we have to see through all the dust that's involved in star formation. But those observations have been made, so we've seen sort of snapshots of the star formation process, which takes hundreds of thousands or maybe a million years at different stages of the process. We've just not, of course, watched it happen in real time like a movie.
All right, we are going to grab the next question. So Noor Ahmed asks, are the exoplanets, oh, I'm sorry, hang on just a second. I'm not hearing that question very well. So the question is from Ragnar, asks, have you ever worked with Roger Penrose or Stephen Hawking?
No, they're sort of a generation above me in age and seniority and so on. And also they've worked most of their entire careers basically in Britain, and I left Britain when I was a grad student after I graduated with a PhD. So I met Stephen Hawking several times, and before he got really kind of too sick to travel or give lectures much. And I only met Roger Penrose once, so they're very esteemed people in the history of astronomy and astrophysics, and I'm glad I got to meet them even briefly.
All right. The next question is from Saib, who asks, can you please explain why we are searching for just human life in exoplanets?
Well, I think we are searching more broadly than that. I think astrobiologists are casting their net very wide. So we're not just looking for human life. In fact, most astrobiologists think it very unlikely that anything like humans exist on these planets. Now, this goes against the sort of tropes of science fiction and movies and TV shows where the aliens very often have human form or humanoid form with slight alterations, bipedal, eyes, ears, nose, just bigger, weirder color skin, and so on. So humanoid is a very unlikely outcome for biology. It's a very specific outcome. Look at the hundreds of millions of species on Earth, and only our humans and our ape cousins look anything like us. So astrobiologists really don't think humans are going to be found anywhere else, or humanoids. They're looking much more widely at what kind of life might form. Now, the most common form of life that we'll find, of course, is microbes, because most of the Earth is microbial. Most of the species on Earth are microbial. There were microbes here for billions of years before there were anything larger than the head of a pin, even in the oceans and then on the land. So that's what life in the universe is mostly going to look like. When life on the universe, if it starts and then if it evolves and becomes larger and more complex, it's really hard to say what it's going to look like. It might not look like anything like any of the creatures we have on the Earth, or it might have some similarities because the constraints of gravity and motion and having to get food sources and travel and inhabit ecological space are similar. So there may be some sculpting of natural selection that leads to creatures that are roughly analogous to Earth life, but not in any great detail.
All right, sorry about that. The next question is from Robert Brady. Has Mars been infected by life from Earth, or really vice versa?
This issue of back and forward contamination with Mars is now becoming important, because we've been sending space probes there for decades, and we think eventually we're going to send people there and have a colony there. So it's an important issue, and NASA actually pays quite a lot of attention to it. Initially, we weren't very careful. So we sent probes to Mars and essentially relied on the fact that they get heated up so much going through the thin Martian atmosphere that at least the outside surfaces get sterilized. But it's not obvious that all parts of the spacecraft are sterilized. For 10 or 15 years now, however, all the missions that have landed on Mars, launched by NASA, have been done so in a sterile way. Now, the outside is always sterilized by its entry through the atmosphere, but the interiors, the spacecraft themselves, were delivered to the launch site having been sterilized and sealed. So essentially, we've been taking pretty great care not to contaminate Mars with terrestrial microbes when we send spacecraft there. That's particularly important when we start looking for life there, because we obviously don't want to look at things that we brought ourselves. So that's been how NASA operates for quite a while, and that will continue in the future. The issue of contamination in the other direction, Mars contaminating the Earth, is of course a concern. If Mars has life forms, if they're alien life forms, not our basis in biology, or even if they are similar to our biology, we could import pathogens or microbes that could cause great harm to the Earth, and nobody wants that. So the protocols have already been established, even though we've not brought back anything from Mars yet, for when we do sample return, probably in 7 or 8 years, how those samples will have been sterilized before they even reach the Earth. And then when the samples are returned and analyzed, they're done in a very sterile way. And we already know how to do this because it was done with the Apollo moon samples. There was no hint of life on the moon because it's an arid, sterile environment with no atmosphere. But those moon rocks were treated at Johnson Space Center to a level 4 biohazard protocol, which is the most severe and strict form of protocol against Ebola or diseases like that. So NASA already has these facilities, and they'll use the same facilities for Mars rocks.
The next question is from World of Science, who would like to know, what is your say on the report of a Pentagon on the Pentagon report that came out about UFOs being spotted?
Right. I've been heavy in the rotation on this. I've written a couple of articles, one for The Conversation, one for The Hill, and I've just written one for the Military Times, actually. So I've written 3 articles about this just in the last month. And I've read the report. It's only 9 pages. So the report we're talking about, it was a highly anticipated report. not actually from the Pentagon. It came from the Office of the Director of National Intelligence. That's Avril Haines in the Biden administration. So it was an intelligence report dealing with military sightings, mostly Navy pilots, of what the military chooses to call UAPs, or unidentified aerial phenomena. So the military has sort of rebranded UFOs as UAPs because of the stigma attached to UFOs and the popular culture and so on, and the disrepute they have among scientists. The report was extremely disappointing. It essentially talked about 144 sightings, again, mostly by Navy pilots between 2004 and 2 years ago. And it essentially could only categorize one of them unequivocally, which was just a deflating weather balloon. The rest it put into vague categories of not enough data, or don't know, or might have been an aircraft from a foreign power. The report never anywhere in it uses the word alien or extraterrestrial, and it doesn't use the term UFO. So the report is mute, or says nothing about the possibility that they're alien visitations, and clearly the military and the intelligence agencies don't think that's a likely explanation. So the report gives no oxygen, if you like, to the conspiracy theories. Quite often then the military is hiding information that aliens have visited the Earth. So the transparency of the fact that they released the report is good, but it's a very disappointing report because there's no data in it. It's just 9 pages long, and no scientists were involved in interpreting it. It was just the military themselves and a few intelligence agencies looking at what they reported. And they just conclude by saying more data is needed, more systematic data is needed, and they promised to report back to Congress in a couple of months on how they were going to gather data in a more systematic way. But they also promised they're going to take the thing seriously. They also say they're going to try and overcome the stigma where military personnel are too embarrassed to report such sightings, and so they get underreported. So they're trying to overcome that so that they at least hear about these. Because from the perspective of the DNI, this is a security issue, a national security issue. If, for example, forget about aliens, if it's a highly sophisticated technology of a foreign adversary like China or Russia, and it's interfering with our airspace and messing with pilots as they fly on missions, then that's a real thing we need to understand. So that is probably what I think is the biggest implication of this report.
The next question is from one of our live participants. And the question is, could we infect Europas with tardigrades? Or could we purposefully send Earth organisms to another moon or planet to try and get them to grow? And what do you think the success of that would be?
Yes, the idea of seeding life on other worlds, it does have a history. So there's astrobiologists and astronomers who've talked about this, and they're pretty divided. I would say my tribe of astronomy is pretty divided on the advisability of this. There are some people that say we have no right to mess with other worlds. I mean, if it's a sterile world like the moon, the odds of life taking hold anywhere are so low that you don't need to consider it. But if it's a place like Mars, or maybe one of the moons of Jupiter that has water somewhere, it's possible we could get microbes to grow. And I'd say the majority of astronomers just don't think it's advisable. They don't think it's smart or even morally or ethically correct to alter another world just because we can. As a scientific experiment, it's also tricky because you don't know what the outcome would be. And probably it's likely to fail because terrestrial organisms were never adapted, never evolved for those alien conditions, and they'd be unlikely to do well. So I think it's moot because I don't think we're going to be doing this anytime soon. But the general consensus is that we shouldn't do it, and NASA, for example, none of NASA's missions have any plans to do this.
The next question is from one of our live participants. When do you think we might be able to get more or better insights about black holes?
Well, the insights are coming as we speak from LIGO and Virgo and other gravitational wave observatories. So LIGO is undergoing an upgrade in sensitivity by a factor of 2 or 3, which should increase its event rate to at least 1 a week. So having had about 15 or 20 black hole merger detections, we're going to go up to 1 a week. 50 a year, 60 a year, and even more if you include neutron stars. So we're going to learn a lot. And also other gravitational wave observatories are coming online. Virgo is now online. The Japanese have a gravity wave observatory, the Brazilians, and so and the Indians, there's a set of observatories that are going to come online in the next few years. And so our sensitivity is going to improve. The positional accuracy of pinning down the source of these events is going to go up. And so the data rate on black hole mergers, just from gravity waves, is going to increase a lot. And that's going to improve our knowledge. That's probably the biggest gain we're going to make in black holes. The other black hole experiments that are going to progress and get better are, of course, the long wavelength, the millimeter wave imaging of the event horizons of black holes, the very spectacular image of M87 from 2 years ago. That will be replicated with the galactic center and probably with another couple of black holes outside our galaxy. But that work is very hard, so that capability is not going to improve as dramatically as our information on black holes that come from gravitational waves.
Excellent. All right, thank you very much. The next question is, again, from one of our live participants. They would like to know about the recent discovery about 4 exoplanets that are 130 light years away from Earth. And we've been finding lots of these. I also saw something about the Von Trapp planets. So can you talk a little bit about some of these recent discoveries of exoplanets?
Yeah, there are so many now that it's hard to keep up because exoplanets are being discovered like dozens per week. And it takes quite a spectacular discovery to even make a news story. So I don't keep up. I don't think anyone can keep up unless you're totally working in the field with every discovery. What's nice about the recent discoveries, there's a lot of these multi-planet systems being found. And the multi-planet systems are often very interesting. They do tend to have a particular property, which is that these are multi-planet systems where the planets are large, Jupiter or sub-Jupiter or Neptune mass, and they're often very close to their star, like hot Jupiters. And because of this, we see resonant orbits quite often, which is a situation where the ratios of the orbital periods of the planets are ratios of whole numbers, which is just a sort of resonant phenomenon of orbital mechanics. We see that in the moons of Jupiter, for example, but it's pretty rare to see it with planets, and it exists only for Neptune and Pluto in our solar system. We're seeing harmonic chains of resonant orbits that involve 4, as in the question, and up to 7, I think, exoplanets in one system, which is quite spectacular. So these are very interesting phenomena for studying exoplanet systems, and for also the implication of how they formed, because they're in orbits that have no similarity to any of the orbits of the planets in our solar system.
The next question is from one of our live participants. What effects would gamma ray bursts have, or a gamma ray burst have, if one were to take place in our galaxy? And then even beyond that, what if it was directed towards us?
Well, I think the distance at which a gamma ray burst could cause problems to the Earth if it were directed right at us does extend out to about 1,000 light years. Now, the galaxy is 100,000 light years across, so that still means it has to be pretty close. So a typical gamma ray burst going off somewhere in our galaxy, even if it's pointed at us, is unlikely to have a significant effect on the Earth. Once it's less than about 1,000 light years, if it's very directed at the Earth, and what we're talking about is the sort of axis of rotation where a lot of the energy emerges, and it's relativistically boosted. It's extremely high energy radiation, focused and relativistically boosted into a narrow beam, and if you're in the way of it, you're getting a lot of energy, even after traveling through space for hundreds of light years. So about 1,000 light years away, we would see an effect. It would affect the atmosphere, or would probably cause major perturbation to telecommunications. It might mess with the ozone layer and cause this mutation rate to spike on the Earth for a few years. Less than 100 light years away, then you have much more serious problems. The direct radiation dosing is going to cause mutations and deaths, and the disruption to the atmosphere could be catastrophic. So these are the prospects. Now the good news is that the incidence of gamma rays burst is very low. In any particular galaxy, the odds that one will go off within a range to be causing damage and pointing at us are such that it only happens once in 100 million years. Now that means it probably has happened in history, but the odds, it's not an imminent or proximate threat.
Excellent, thank you very much. The next question from one of our live participants is, how would our solar system change if we had planets in the gaps between the planets in our solar system? So I guess, we could talk about a lot of different things with regards to this. He says, what would happen if we added planets? That seems unlikely. But, how many planets can a solar system have, and how close can they be?
Well, it's an interesting question because planetary scientists have considered this question. And it has an interesting and simple answer. The answer is that as big as the distance between the planets is, or are, in our solar system, and you know that the distance between planets compared to their size is factor of millions, tens or hundreds of millions. The planets are tiny. They occupy a tiny fraction of the space. But if you do the orbital dynamics and you do a little gravitational experiment, our solar system is full, so to speak. And so the answer to the question is, if you dropped a planet, just a small, modest Earth-sized planet or Mars-sized planet, between any of the terrestrial planets, like between, halfway between Mercury and Venus, or between Venus and the Earth, or between Earth and Mars, it would cause major disruption. Over time, it would disturb or perturb the orbits of the planets that it was between sufficiently that one or both or all three might get ejected from the system. So that's a very interesting scenario, and people have played this out in computers, and they're pretty sure that it's the case. So as empty as the solar system is, it's dynamically and gravitationally full. You could not add another planet. And if you did so, for example, in some bizarre way, there was another star system near us, and it had ejected a planet, and that planet fell into our solar system and took an orbit there. Yeah, that would cause major disruption. So the solar system is full, and in general, solar systems cannot get tightly packed because the gravitational interactions between the planets can cause resonances, and those resonances are nonlinear, and they can lead to the orbits being perturbed and eventually unstable, and that leads to the ejection of one or more of the planets. And we've started to understand how this happens. So it's very unusual to see tightly packed solar systems, even among the exoplanets.
The next question is, what do you think about the Drake equation in terms of exoplanets and life on exoplanets?
So the Drake equation was a formulation by Frank Drake from 1959, I think, a conference at Green Bank Observatory, a radio observatory in Virginia. He was a young postdoc, and he was running a Life in the Universe meeting when astrobiology was not a very big field. And he went to the blackboard, and he essentially put the factors of the equation that would be named after him on the board as a way of organizing the thoughts about how to look for life in the universe and intelligent life. And it's been a guiding framework for astrobiology, and what's happened in the time since he first proposed it is that we've measured some of these factors. So we know the rate of new stars forming. We pretty much know what fraction of stars have planets, and we pretty much know what fraction of those planets are Earth-like or habitable. So 3 of the terms of the Drake equation have been measured. That's great progress. The trouble is the last 4 terms have not been measured at all, and really haven't got very far in measuring them. And that is, what fraction of habitable planets actually develop biology? In what fraction of those instances does the biology become advanced and have intelligence attached to it? And in what fraction of those cases does that intelligent life develop technology, the ability to travel through space or communicate in space? And the final term, what's the longevity of a civilization in that state? We don't know those 4 factors at all. So the product of 3 things that you know and have measured multiplied by 4 things that are indeterminate is indeterminate. So the Drake equation is still indeterminate, even though we've made progress after 60 years.
The next question is from David, who's on with us live. Do astronomers use tools akin to time-lapse photography in their observation work?
Yes, astronomers do the equivalent of time-lapse photography. They clearly make movies of moving objects in the sky. They make time-lapse movies of the sky on successive nights over a whole month or a whole year for slow-moving objects, or just for looking at phenomena that change very slowly. It's a pretty standard tool of astronomy now that we can make images of large chunks of the universe to gather that data over a time sequence and then present it as a sort of time-lapse sequence of events. Unlike time-lapse photography in the everyday world, though, the timescales we're talking about are played out over a long period of time. So except for rapidly moving objects like asteroids, time-lapse photography is generally used over months and years.
Excellent. The next question is from one of our live participants as well, and I will switch to I'm finally getting caught up with questions, so I'll switch over to some emails that people have sent in shortly, and my apologies, I'm just trying to kind of keep up. Spot Zen would like to know, will we ever start using cryogenic sleep for human space travel?
It's likely that that's almost the only way that humans could get to another star system in a plausible way, is if we develop the ability for suspended animation or cryogenically induced sleep. The technology of that is advancing based on the medical field, because people suffering near death or brain dead experiences from being submerged in ice water or whatever, it's been learned that by taking people down to very low temperature, you can still their biological and metabolic rates by a large factor. It's also been experimented with animals, with pigs, rats, dogs, I think, that if you can replace you can combine cryogenic methods with replacing body fluids with things like glycol to restore, to take an animal into a hibernating state essentially, and then revive them after, a few cases, weeks or even months, with moderate success. That is not complete success. Some of them die, but some of them come back okay. So there's research in the medical field that is advancing the idea of cryogenic freezing and suspended animation, but it's very early stages and very primitive. But the truth is that with any conceivable technology and new propulsion systems that we don't have yet, the energy costs of moving outside our star system to another star are prohibitive, and the best we can hope to do is get to a few percent of the speed of light. And of course, at that speed, it's centuries to the nearest star, and so you would literally, unless you just had a huge starship where people were living and dying and living their lives, and a new generation was the people who got to that star system, if you wanted the original people to get there, you would have to have these methods perfected. So I'd say we're decades and maybe much longer from these methods. And some medical experts think that it's not possible, think that it's simply not possible to cryogenically freeze a human and revive them. They think that despite that, the aging process at some level continues.
The next question is from an email. This is from a few weeks ago, or I guess a couple of weeks ago. Martin Gillum emailed and asked that they, or said that they just heard on the radio that the Hubble Space Telescope had a computer problem that prevented it from transmitting information for a while. Are there any updates on this, and is it feasible to repair the Hubble?
Yes, I think that they pretty much have repaired the Hubble. The fix happened quite quickly, but all the tests to understand why it happened, to try and make sure it didn't happen again and make sure that data was not being compromised when they started operations, took a lot longer. So I don't even think normal operations have yet started. But it's a problem that has a recovery, and I think the recovery's been executed. The issues we're dealing with the Hubble are it's a vintage telescope, 30 years old. Systems are decaying and degrading. Remember, there's a lot of cosmic rays out there, so the computer systems and the solar panels, almost all parts of the telescope are showing their age, losing gyros, of course. That happens more often than it would on the ground under test conditions. So, it's a real question how long the Hubble is going to last, and there's no way to fix it. There are no more servicing missions planned at all. So when Hubble dies, that is it. And however it dies, it's not clear how it's going to die. Probably by gyro loss than by computer loss or solar panels degrading.
The next question is from email. Wendy Traver asked, could inflation have been the freezing out of the strong force from the other forces, as they read in an article, I guess some kind of cosmology article?
Yes, there's a hypothetical time very early in the universe when all the forces of nature except gravity were unified, and these are supersymmetry theories. So that is the strong force, the weak force, both of which operate within the atom, and the electromagnetic force. So there are supersymmetry theories that indeed could be the mechanism when the supersymmetry is broken as the temperature falls and the universe expands. It's possible that this is a mechanism for inflation. But it's not sufficient. The theory is not well developed because there's also ideas that inflation is driven by quantum fluctuations in the vacuum, or the false vacuum as it's called in physics. And it's very hard to distinguish these mechanisms. So the mechanism of inflation, the cause of the inflation field, is not known, and there are many different theories for it. And we're not really actually very close to knowing what it was, because there's very few experimental diagnostics for the inflationary era.
The next question is from Andrew Johnson, who's on with us live. Is it possible for there to be a truly black object in the physical universe, something that absorbs all radiation?
It's possible, but actually normal materials don't take that property. I mean, there are incredible materials to be created in the lab, black materials and coatings that absorb 99.999% of the light falling on them. That's fantastically black. So the measurement of the reflectivity of an astronomical object is called its albedo, and the way it works is that albedo ranges from 0, meaning it absorbs all the light that falls on it, and then it's totally black, to 1, which means it's totally white or reflective like a mirror. And in normal astronomical objects, the average albedo is about 0.3. They're just sort of gray-looking rocks. That's a typical albedo of a rock from the Earth or the Moon or any rocky body. There are some objects that are extremely dark. So the darkest objects have albedos that mean they are absorbing 80 or 90% of the light that falls on them. And that, to our eye, would look pretty black. So that's about as far as it goes with rocky objects. And that's not because they were burned or charred. That's just because they typically involve a lot of graphite and carbon-rich material. And so it's sort of like jet black. It's like looking at a carbon surface. So that's as high as albedos go in any astronomical object. So not totally jet black, but pretty close.
All right, and it is 10 till, and if I recall correctly, we need to end a little early. And so I apologize for our technical difficulties, which made us start a little late. But we have some good news to report. Our servers are coming back online. Our Teach Astronomy website is back up and running at a basic level, and we should be, for those of you in our class who have had trouble getting access to the textbook, that should be coming up and working again. All those features and additional materials should be coming up and back online soon. And then we also have another live session in just, it really is less than 2 weeks, because it's on a Monday 2 weeks from now. So we are looking forward to seeing you all then. And thank you for your patience with our technical difficulties today. I'll let you say goodbye, Chris, and then I will log us off.
Okay. Well, thanks everyone for your excellent questions as always. And as Matthew said, we'll be back with you in less than 2 weeks.